So let's recall what we did yesterday, at least a bit of it. We went over Green's theorem a little bit more. So I'll scroll up to Green's theorem. Green's theorem relates the line integrals to surface integrals. That's the overall idea. Specifically, Green's theorem says you can write a work integral, this integral of m dx plus n dy, as a surface integral where you're integrating the kth component of curl. That's what this part here is. Again, we'll define curl, I think in section 16.7, a little bit later on. But this is the kth component of curl. Green's theorem also allows us to write the outward flux and relate that to a double integral of divergence. So this term here, this del m del x plus del n del y, this is known as the divergence of a vector field. So, but again, the idea is we have a line integral and we can turn that into a surface integral and vice versa. We went through the derivation of one of these. I think it was the circulation one. Kind of said, look, the circulation around the curve should be, adding up the circulation along around each of these mini little rectangles in here. And if you do that, you get a certain term, this kth component of curl, and you add that up over the entire area of the region, and that's your double integral. Yeah, so we define that, we define divergence. Then we went through some examples. Right, we saw that in this case, you could just get the setup for a vector field and you can have a curve. Well, sometimes that curve is broken up into two pieces. Sometimes it's it'll take a lot longer to set it up in terms of a line integral. Maybe there's multiple line integrals, but if it's a nice region, then you can just set it up into, a single double integral. We also saw that depending, or if you're given a line integral just like this in some curve, then you can, and you're not necessarily given a vector field, but you can take this information and sort of pull out of it a vector field, right? Depends on how you want to look at it, but we can get a vector field out of this line integral and use Green's theorem in either form to write this line integral as a double integral and make it a little bit easier. Right, so we saw this and we kind of picked out two methods for each of the parts of Green's theorem. Either way, you could get a different vector field, right? The first one was here. Second one was here. And the point is, either way, you get the same integral. You get a double integral of 4. And so we just need to set up the bounds. And that's where we left off. So before we get going on more examples, I mentioned something about usually a worksheet or something like that, that we can check sort of our intuition of divergence and kth component of curl. So here are 4 vector fields drawn out, sketched out. It's a little awkward because I can't quite show all of it. So we'll just do this. A is the vector field Cx, Cy. B is the vector field negative cy, cx, and then we can kind of see the last two when we scroll down. Okay. So let's look at these first two vector fields here. What we first want to look at is the divergence of the vector field. So divergence, again, I can kind of scroll down. This already gives us an answer, but the divergence is this del m del x plus del n del y. So for a positive constant, if we come back up here, again, write del m del x plus del n del y. If we look back up here at the first one, we would get a divergence of, just like we saw, 2c, right? If we take the derivative of m with respect to x and n with respect to y, we get c for both of them. So what that says is, this vector field is kind of, again, for a positive constant, this vector field is kind of diverging, right? This would be a positive number for c greater than 0. Let's just assume that for right now, because I think that's how all these pictures are drawn. So what that means is, more particles are kind of flying away more than they're flying to a specific object, right? So I tried to draw this out here. So if you were to take any one of these points, again, maybe we could just draw it here, say, take this point right here. Well, there are smaller vectors pointing towards it and larger vectors pointing away from it. And so I picked this one specifically on the x-axis because there's no kind of vertical movement or anything like that. But this particle would just move only on the x-axis. And it would move continually to the right. Right? And so if we, again, go further back, you could see the same phenomenon. And if you go on the left axis, you would see that same sort of thing, right? You would see vectors kind of pointing to the left, but the further out vectors are pointing or are larger than the inner vectors. And so what this means, at any given point, sort of the vector field is diverging away from it. It's pointing away from it instead of pointing towards it. So now if we come over to this one, our vector field is negative cy plus, or comma, cx. And if we were to look at the divergence, well, we would get negative, or we would get del m del x, but that's a 0. And del n del y is a 0. So altogether we get 0. So what that means is at any given point with this vector field, there's nothing pointing overall away from it, and there's nothing pointing like overall towards it, right? So if I looked at this point here, I would have a vector of the same magnitude pointing that way as I would kind of have pointing this way. Right, so their angles kind of cancel out. And so yeah, I mean this is kind of the picture, right? It's not like I have vectors pointing a bunch this way or anything like that. What it's saying is everything that kind of moves into that place is like equally replaced. It's not like it's flowing, faster going away or anything like that. So divergence 0 at every point in this plane. Which I kind of regret. Wish I would have written these up here. Okay, and these last two examples, they aren't actually that interesting either. It turns out divergence is 0 for both of these too. Right, in much of the same way. Well, maybe not for this right one. But for the left one, again, much of the same way. If we zoom in here, we take any of these points. So this point here, right? What's going on is that if you pick any fixed y value here, your vector field is pointing at that rate, right? So the larger the y values, the longer the vectors. The smaller the y values, getting close to 0, the shorter the vectors. And if you go negative y, then you get the opposite direction. Right, so if you were to take a point here, you have a vector pointing to it, but you have that same magnitude vector pointing away from it. And you don't have any sort of up or down motion here. But this is, again, kind of an equal velocity pushing vectors to a point and an equal velocity sort of pushing vectors past that point. We would get the same thing over here. Granted, it would be a little bit more tedious to go through this calculation. It turns out we would get 0. Go through, try it out if you want. These are partial derivatives here that you're taking. It's a little bit annoying, but you find out that everything kind of cancels out here. And for roughly the same reason, right, as before. Okay, so this is divergence. Again, it's the idea that if your vector field is pointing away from you more than it's pointing towards you, or vice versa, then you're going to have some divergence. Is this still section 16.4? It is. It is still section 16.4. So we are going to be a bit behind, but I did want to kind of cover some of this stuff. And then there was this other thing, the circulation density, or the kth component of curl. So I'm going to write that they're the exact same vector fields. So we'll write them up there. In circulation density, kth component of curl, if we remember, should have been dn dx, del n del x minus del m del y. Right, so if we compute this for the first vector field, we should get a 0, right? Because del n del x, del n del x there, that's a 0. Del m del y, that's a 0. So we should get 0 here. And the way to kind of figure out the circulation density, it's a bit awkward, but the idea is at a particle, what you want to do is think of it having a bunch of like little spokes pointing out of it, right? Spokes pointing in different directions. Usually 4 is kind of the idea. This is nice to visualize. And then you see what the vector field is doing as it pushes against it. So again, we'll zoom in here. And if we were to take any point, kind of draw spokes out, then what we're going to see is that, the vector field is going to push evenly on this side as it will on this side. So it's not going to turn it at all, but it's going to kind of keep pushing the particle away and away. And these other two spokes, well, those aren't going to really affect, kind of the turning of this particle. So since this particle doesn't turn, and since none of these particles would turn, that means the circulation density is 0. So it's kind of the rate at which these particles turn. So in this case, again, if we were to compute the circulation density, right, we have del n del x, which is a c, minus del m del y, which is also going to be a c in this case. So we get a 2c for this. So what that means is for c greater than 0, we have kind of a counterclockwise rotation. So let's look at one of these particles here. If I draw my spokes out again, well, we see that on the outside, we have a greater force pushing against it than on the inside. So what that means is that's going to start pushing this in a counterclockwise direction and start rotating it as it's moving around in this vector field. So it's going to have kind of this counterclockwise motion to it. Coming down here. Again, if you do circulation density, you should get 1 in this case. Right? It's del n del y minus del m del x. And again, so this says we should have another counterclockwise sorry, those are all clockwise rotations. Did I write this wrong? Huh, okay. Sorry. Change everything I said about clockwise and counterclockwise too. Well, no, hold on a second. This is counterclockwise, isn't it? Yeah, that's counterclockwise. But this would be clockwise. So actually a bit confused by this now. I'll look into this later. That's interesting. Anyways, if we were to draw the picture, again, we take a point, we draw out its spokes. We have greater arrows on the top than on the bottom. And so this would be spinning it, I guess, in a clockwise motion this time. So maybe the sign of the circulation density doesn't actually tell you what way it's spinning. Oh, dm dy minus dm dy. Yes, yes, yes. Oh my goodness. Thank you, thank you, thank you. Right. This is I was yeah. Right, it's del n del x minus del m del y. Thank you for saving me here because I was going a little crazy. Awesome. Yeah, so we should get a -1, which means the clockwise motion and everything's back to being right in the world. Great. But again, no matter where we see this point, we see that, these vectors are kind of pushing it in a rotational way. And if you were to also look down here, even though the vectors are pointing in the opposite direction, if you draw your spokes, again, there's larger vectors on the bottom now, smaller vectors on the top, but that still pushes it in a clockwise rotation. So again, circulation density is like kind of how much it turns, particles turn on their own, while divergence is how much like the particles are pushed away from it or pulled into it. And then this one is a bit more interesting. we still have this kind of vortexy pattern, and this is much more of a vortex now because it's quicker on in the middle than on the outside. But it turns out the circulation density of this is 0. So what that means is if you were to take a particle, any particle, dry out the spokes, even though there is greater force on the inside than there is on the outside, this particle basically keeps its same orientation no matter where it is in the plane. So what do I mean by that? Let me draw this one as a black spoke. And so the idea is that this black spoke is going to be pointing exactly in the northwest direction, no matter if the particle starts here or if it starts somewhere else, right? So if you were to draw the same thing and you were to kind of see it travel around this thing, this vortex, its spokes wouldn't turn. It would still look like that, even though it's moving around. And so that's because like the vortex is kind of trying to turn it in a counterclockwise direction, but the speed of the vortex is pushing it in a clockwise direction, and those two kind of spins cancel it out. It's kind of weird, but yeah, this is one of those interesting examples. Cool. So again, hopefully we understand a little, maybe we understand circulation density and divergence a little bit more now than before. But if you're more confused, that's also natural. I just wanted to write these down and give you kind of an idea of like what each of these are visually. So you can also go play around with some of those vector field visualizations and kind of guess at what's going on there too. Okay, are there any questions? All right, doesn't look like it. It's gonna be a bit annoying. So I think what I'm going to do is upload these 2 pages and then probably delete them from the notes because this sort of sliding thing is, I think, going to annoy me too much as we go forward, but we'll see. So you might not be able to get to ask questions on those pieces of paper after today. So just be aware of that. Or at least like we can pull it up on Canvas, but they won't necessarily be in these notes. Okay, so there was maybe one more example that we could have covered in section 16.4, but it's kind of the same thing that we would have gone over. It's here's a line integral with some stuff in front of dx and dy, write out the double integral and evaluate it. So again, a lot of the examples are kind of similar to that. If I find that, there was something else I was kind of missing, then, maybe we'll go back and see, but didn't look like too much. So let's move on to 16.5, so we're not too far behind. And this is parameterizing surfaces and surface area. Not parameterizing surface area, but surface area is a different concept. Okay, so we talked about parameterizing curves, right? So a curve is some r of t, it's one variable, and in 3 dimensions, we said it was something like x of t, y of t, z of t. right? And then we want kind of a finite curve length. So we say t from A to B. Okay, so this is a parameterization of a curve. Usually it's also denoted C like that. But now we want to look at the parameterization of a surface. So like a plane, or at least a chunk of a plane, or a cone, or anything like that. So what we say is, for a surface S, we have R of u comma v are going to be the two placeholder variables for now. And we write this as, again, kind of our x of uv, y of uv, z of uv. I'm not going to use x, y, and z in this case. Actually, I am going to use x, y, and z in this case. Sorry, I wasn't looking at the right place in my notes. So I mean, this is basically the idea. We just bumping up one variable. And we need some bounds for each of those variables. So something like this. Again, just like kind of before, if we were looking in the t coordinates, this would be a line segment. If we're looking in the uv coordinates, this is a rectangle. But again, this could be any sort of surface that we see out in Cartesian coordinates, or polar, or cylindrical coordinates, or spherical coordinates. So let's just take a moment and go through an example and kind of see how this works. This is going to work mostly the same as parameterizing a curve. We want to start out with some sort of r of blank comma blank, and then we're going to figure out what our variables are kind of through the way. And the place to start is kind of always x, y, and z, and then we can use some substitutions. So our first example is parameterize the cone z is equal to the square root of x squared plus y squared. Between the planes, z equals 0 and z equals 1. So this is our data. And again, we want to take this parameterization up here and figure out two variables, which we can write this in, and two nice variables so that we can also have this kind of rectangular bounds. Okay, so given this information right off the bat, we can see that we can already get rid of this z here, right? We can change z to square root of x squared plus y squared. But the issue with just leaving it with as the variables x and y is writing some bounds, right? A cone, it turns out that this is the 45-degree angle cone. Something like this. And the domain on this isn't rectangular, right? If you were to look at the xy domain, right, the kind of shadow this cast in the xy plane is a circle, but a circle isn't a rectangle. So that's kind of one tell that you can see that maybe these variables aren't the best variables to use. hopefully I've kind of talked long enough that maybe a certain coordinate system has popped up into your head. So the thing that deals with circles very well is the polar coordinate system. Right, and if that didn't, if circles and all that didn't clue you in for polar coordinates, maybe the square root of x squared plus y squared clues you in, because this is kind of the we don't want to deal with that in Cartesian, but polar coordinates, that's very easy to deal with. So if we were to switch this over, we have r cosine of theta, we have r sine of theta, then we would have a square root of r squared. That's just r, since r is, a non-negative number. And now we have a really nice parameterization in terms of two variables, no square roots running around, none of that. And we can probably figure out some bounds for r and theta. Right, certainly 0 to 2 pi for theta. Again, the picture doesn't quite show it, but if you're not so sure that 0 to 2 pi would work, go to GeoGebra, graph out this cone here, check between 0 and 1, and really see that this is a cone centered about the z-axis. And then we need our our r bounds. And you could get this one of two ways, right? You could look at the shape and you could say, well, this shape, it goes from 0 to 1. That's kind of the idea here. Or you could come back up to here and you could see that z is actually equal to r. And so you can plug that into the z bounds that you had here. Right, since z is equal to r in this case, and z is between 0 and 1, then r should be between 0 and 1. So overall, this is our parameterization of the surface. We can write r of r comma theta, which is a little bit weird. Make sure to write down your vector sign. But this is a parameterization of that cone. All right, any questions about this example? Okay, so no questions. So let's move on to a bit of theory. And again, this is how you really should set up every single parameterization problem. You really should say r of blank blank is equal to the vector xyz. Plug in information that you know, figure out what might be the best coordinate system if Cartesian coordinates are the best, or if polar coordinates, cylindrical coordinates, or spherical coordinates, and then what two variables out of those coordinates will best suit you, right? So those are the things that you kind of need to go through and set this problem up. But this is your starting point, every single parameterization problem. Okay. So we're going to get into a bit of theory. So given a parameterization, r of uv parameterization of a surface, we have two derivatives for r. So now we have partial derivatives, del r del u, or another way to write that is r vector sub u. But this is, the vector of those partial derivatives. And same thing, but for the vector v. I'm not going to write out the vector part of this, but sorry, I might have said vector v, the variable v. I'm going to skip writing out that, but it's the same thing. So now we have two partial derivatives. Here's a definition. A surface given by a parameterization R of uv is called smooth if each partial derivative if the partial derivatives are continuous and the cross product of these partial derivatives is not the zero vector at every point. So these are the two conditions to actually have a smooth surface. We probably won't do a whole lot of these computations for smoothness necessarily, but get used to it. You will have to do some of these computations. So kind of a problem that we will go through is parameterize a surface and compute this cross product. So then you'll have to take two partial derivatives, then you'll have to take a cross product of those two partial derivatives. So if you forgot all about the cross product, remember it because we're going to need it. So if we have a smooth surface, I'll just write it out like this. The surface area of a smooth surface is the following. It's a double integral over R. I really kind of don't want to write R, so I won't. This is a double integral over the surface S of the function 1 d sigma. Okay. So I'm happy to write it this way. So this is kind of like, okay, well, what if we were to write it, integral over the curve ds? That's kind of what's going on here. This sigma is replacing the ds here. If we actually wanted to go through and compute this integral, well, we need to change our bounds and we need to change kind of our variables here. So we would change this into a double integral of R over R of the function 1 RU cross, or the magnitude of RU cross RV dA, but there's a little bit of a catch here. This R and this dA these are written in terms of U and V. So, right, these would be UV bounds, and this would be something like DU, DV or DV, DU. So the reason I wanted to write it first as this double integral over S d sigma is because this really is kind of a change in coordinates, right? This is a substitution here that we're going from units of the surface to units that we can kind of compute. And this magnitude of the vector, this is our Jacobian. right? This is that scaling factor that we always need to add in there. So again, kind of like you're replacing this d sigma with this term here. And this is the first introduction to surface integrals, which is, I think, the next section. This section is all about just writing out surface area and parameterizations of surfaces. So I need to write out a warning here. If you are using a different coordinate system, say r theta as uv, right? Like in our first example, let's say we had r and theta. Do not use r dr d theta as your switch into this dA. So again, do not use this. Always use the cross product or the magnitude of the cross product. Sometimes it might just be r, but it also might change. Right, so this isn't just like a normal switch to polar coordinates or a normal switch to cylindrical or spherical coordinates. This is, I'm living inside of that coordinate system, but I might use, two different coordinates. I mean, you could have potentially used like z and r, and again, this r might not have shown up, or you could have potentially used z and theta, and this r might not show up. It might be a z or it might be something else. The point is, we always want to use this magnitude of the cross product. So there's a lot of things to keep track of. But if you really just stick to this formula, this surface area formula here, you shouldn't go wrong with any of this warning stuff down here. So let's do an example. And I think we're going to continue this example into tomorrow. Maybe not. Maybe we'll just do a another parameterization example. This will continue on until tomorrow. So x squared plus y minus 3 squared is equal to 9. Right, so this is a cylinder that is kind of shifted off the x-axis a little bit, or sorry, the z-axis a little bit. And then we want z between 0 and 5. So this is a cylinder of height 5, of radius 3, but it's shifted off of the z-axis a little bit. So again, we can try to draw this thing. Something like this, 3, height 5. Let's say it's roughly correct. One thing to notice here is that z is not part of the equation. So it is a parameter, or at least it's going to lead us to one of the parameters. So this isn't, a fully honest sentence, but it gets us thinking in the right direction. So if we're just looking at this, again, we have some sort of R of blank blank is equal to XYZ. We have a hunch that Z is going to play nicely with this, so we'll keep that along for the ride. But cylinders, again, cylindrical coordinates is kind of where our mind should go here. And we can use the equation above to kind of help us out if we wanted to. But I think a nice starting point might be this R cosine of theta, R sine of theta, Z. So now we're doing a switch first to our coordinate system, and then we're going to use this equation to kind of narrow us down. I'm going to skip a lot of this, but the idea is that we want to substitute in R squared cosine squared plus quantity R squared sine squared minus 3 squared equals 9. And then you want to do a bunch of algebra. Simplify. Eventually you get to R times R minus 6 sine of theta is equal to 0. So again, bunch of algebra. I'm going to skip it for time's sake. You get R equals 0, which is not really a solution that we care about. And then we also get R is equal to 6 sine of theta. So what this says is for this cylinder, we can replace R in terms of theta. And so our parameterization turns out to be in terms of theta and Z. Let's bring this thing down here. Replace R with cos or R with 6 sine. So we have a 6 sine of theta cosine of theta, comma 6 sine squared of theta, comma Z. So again, this is a nice example where we see that we're using cylindrical coordinates, but we're not using R and theta in this case, we're using theta and Z. The last part is finding out bounds. Luckily, we already have Z bounds from above, up here. And our theta bounds, we'd have to play around with a little bit. And for the sake of time, I'm just going to write them down. 0 to pi would be our theta bounds. Again, you can get them from the picture. You can get them algebraically using this formula too, or using a different formula, but I think I'll stop here and say this is the parameterization of the surface. Cool. So tomorrow we can set up a double integral, a surface integral involving finding the surface area of this. We can check out the Jacobian and all of that. Maybe we won't because this is like a messy example, but shouldn't be too bad. Okay. I checked on the quiz. Quiz looks fine for today, even though we didn't get through all of the surfaces and area part, or sorry, we got through Green's theorem a little late, but quizzes look fine. again, homework 10's on Friday. We should be fine for material there, but I'll double check tomorrow. So yeah, I will see you guys tomorrow.